G'day, let's look at alkenes. So alkenes are compounds that have double bonds. They're organic compounds with double bonds between carbon. Here's a couple of examples. There's geraniol, which is from certain flowers, including roses and geraniums. And the one below that is myrcene, which is from citrus fruits like lemons. So each of those compounds have double bonds between carbon atoms. So we call these types of compounds unsaturated hydrocarbons because instead of being fully saturated with hydrogen, they have double bonds between carbon. That means that we could potentially add more hydrogen to these molecules to get alkanes. So they contain at least one multiple bond. Now every time we go from an alkane and we introduce a double bond rather than just single bonds, we're removing two hydrogens to form that double bond. And so, whereas the formula for alkanes is CnH2n plus 2, for alkenes, it's going to be CnH2n. So this is the general chemical formula for alkenes with one double bond. If we have more than one double bond, we remove two hydrogens for every extra double bond we put in place. So if we have a triple bond, that's sort of like having two double bonds, two pi bonds. We'll go through that more in a moment. But so the molecular formula for an alkyne, which has a triple bond, is CnH2n minus 2. So for example, acetylene is C2H2. Okay, so alkenes and alkynes are really important molecules. They're more reactive than alkanes. They actually do sort of more interesting chemistry. So an alkane like ethane, really about the only thing we do with it is burn it or reform it into other hydrocarbons through very high temperature processes. Whereas ethylene can do a lot of chemistry and it can be used for other purposes. So ethylene is also used for ripening bananas. Alkynes, the simplest of which is called ethine, or more commonly acetylene. Acetylene is used in welding, so you might have heard of oxyacetylene torches, which burn in a very hot flame. So the bonding in unsaturated hydrocarbons involves a pi bond. So a pi bond is the edge-on overlap between p orbitals. So we've got sideways overlap between p orbitals. And so that pi bond has interesting chemistry and imparts interesting properties on the molecule. So it's a covalent bond. So the electron density of this bond is above and below the plane of the axis that joins those two atoms together. And so to get to this sort of arrangement, we have to do hybridization of the atomic orbitals of the carbons that are involved in that bond. So if we take the 2s and 2p orbitals, and we make them so that all the electrons are filling each one of those atomic orbitals, and then we hybridize them to get to the right hybridization for an alkene. We would have sp2 hybridized orbitals. So we have one s orbital and two p orbitals combined together, and that leaves one 2p orbital left over, and that's the 2p orbital is what undergoes this edge-on or pi bonding. Okay, so pi bonds are electron-rich, and that electron density is not between the two positively charged nuclei, so it's a little bit sort of more reactive. So they're generally weaker than sigma bonds, which are the strongest type of bonds, therefore they're more reactive, and they behave as nucleophiles. So this term nucleophiles is really important in organic chemistry. So nucleophiles means nucleus loving. And remember, a nucleus has a positive charge, and so therefore nucleophiles are trying to react with something with a positive charge, or they're trying to react with something with a partial positive charge because they really want to access that positive charge. Okay, so having a bit of a closer look at the bonding within alkenes and other unsaturated hydrocarbons, the sp2 hybridized geometry means that we have three bonds in the plane of that atom, or the two atoms that are bonded to each other. So there's the three bonds there, one to a hydrogen, one to another hydrogen, and one to the carbon that's bonded to, in the case of ethene or ethylene. And then we have a leftover p orbital. So this p orbital here can overlap with the p orbital on the carbon next door to form this pi bond. So we've got one electron in each of these p orbitals that are creating that pi bond between these two atoms. And so really when we bring the atomic orbitals together, we start with something that looks like this situation here, but after we combine them together to make the molecular orbitals, we get a pi bond or a pi electron cloud that extends between those two carbon atoms but above and below the plane. So if we look at alkynes, this is very, very similar. We just have two sets of p orbitals that are orthogonal to each other that are involved in two sets of pi bonds. And so in this case, we're promoting up an electron. So we have a even distribution of electrons between the 2s and 2p orbitals. And then when we hybridize those together now to get this triple bond, we choose to hybridize as two sp orbitals and two remaining unhybridized 2p orbitals. And so here we would have one of the sp orbitals is going to be pointing in one direction. The other sp orbital is pointing away from that at 180 degrees. So unfortunately, the color of these is blue in both cases, but those two are different sp orbitals. So that's one sp orbital there and one sp orbital there. And then orthogonal to those, we've got a 2p atomic orbital in red, and that extends above and below the plane there, and a 2p atomic orbital in green there that it extends towards us and away from us, as it's shown in that picture with the balloons. And so below the balloons there, we've got a depiction of the atomic orbitals drawn out, showing which ones are unhybridized and which ones are hybridized. Okay, so we've just lost a little bit of that symbol there. So we've got two pi bonds in an alkyne, and they're orthogonal to each other, but they're both outside of the plane or the axis that joins those two carbon atoms together. So the bond angles in an alkyne are 180 degrees. So they're completely linear. So when we draw an alkyne, we will draw it like this with the substituents at either end pointing 180 degrees to each other. Okay, so let's look at the structure of alkenes in a little bit more detail. Unlike alkanes, which only have a single bond between the carbon atoms, an alkene has a double bond, and that second bond, this pi bond, restricts the rotation around that carbon-carbon bond. So if we try to rotate between those two carbon atoms, we're going to break the overlap of those p orbitals because they're no longer going to be able to interact with each other in this sideways overlap. So that makes it impossible to rotate around that carbon-carbon bond without breaking the pi bond. And so that has implications in terms of what we call stereochemistry. So stereochemistry is the three-dimensional arrangement of atoms within a molecule where we could have two stereochemical isomers that only differ in the three-dimensional arrangement of the atoms and not the actual connectivity of which atom is connected to which. We also sometimes call these geometric isomers. So for example, if we have this alkene here, it is different to this alkene here. So we've got these two methyls on the same side. Whereas in the other molecule, we've got the two methyl groups on opposite sides. And so they're actually different compounds or different stereochemistry or different stereoisomers. So we need a way of talking about these, and the simplest way to talk about many alkenes is with their cis or trans when we have that possibility. So if they're on the same side, then we call them cis. So cis is same and trans is opposite. And I think this is fairly easy to remember because cis starts with that s sound, cis, same, whereas trans is opposite. And I guess there's many situations where we talk about things being trans as being opposite in some way. However, sometimes we have more complex alkenes where we can't use cis and trans notation to tell us what isomer we have. So then we use what's called EZ notation. So EZ notation becomes important because sometimes we may have substituents on an alkene that we have more than two substituents. So in that case, what are we talking about? Which ones are on the same side, which ones are on opposite sides? So EZ notation is a way of telling us which alkene we have when we have more complex situations. Okay, so to assign EZ notation to an alkene, firstly we need to split the molecule in half down the double bond. So if we have a double bond like this, and we have A, B, and C, and D, then to apply the EZ notation, we're going to split the molecule this way. Okay, we're going to look at A versus B first, and then we're going to look at C versus D, and we're going to look at which one is the higher priority on each side of that double bond. Okay, so to assign priority, we're looking for what substituent has the highest atomic number. Now, here it says H for highest. I think it's probably less confusing to use 1 for highest, and instead of L for lowest, we use 2 for lowest, and that just avoids any ambiguity around H also standing for hydrogen. So the priority increases with atomic number, and we start at the atom that's directly attached to the alkene first, and then work our way out along a chain if we need to, according to when we find the first point of difference. Okay, so here we've got arranged a small subset of groups that could be attached to an alkene in terms of increasing priority. Hydrogen's always going to be the lowest priority. And then in this particular set, carbon is going to be next, then nitrogen, then oxygen. And then looking at the halogens, chlorine is a lower atomic number than bromine. And so that would be our priority order. Bromine would be the highest priority, chlorine next highest, and so on. So if two atoms are identical in terms of their priority, then we move out along the chain until we find the first point of difference in that chain. And repeat this for the other side. And then we look to see, are the two highest priority groups on the same side of the double bond or on opposite sides? If they're on the same side, we call that the Z isomer. And if they're on opposite sides, we call that the E isomer. And a little tip for remembering this is that Z is the same side. They're on the same side. They're on the same side. So just think of it in terms of maybe a Dracula accent or something like that. So Z isomer is on the same side. So we're going to get to a situation that either looks like this on the left here for Z, or we're going to get to a situation on the right where they're on the highest priority groups are on opposite sides, and that will be the E isomer. Okay, so let's have a look at a couple of examples. So if we look at this compound here, we've got the priorities are first assigned on the basis of the atomic numbers. So let's look at the left-hand side first. So if we look over here, we've got a carbon atom versus an iodine atom. Iodine has a higher atomic number, and so iodine will get the higher priority and carbon will get the lower priority. And remember, we've split the molecule in half, looking at one half and then the other. So now let's look at the other half of the molecule over here. So we've got a fluorine versus a hydrogen. And so fluorine has a higher atomic number, and so it's going to have the higher priority. Now we've got the highest priority group on this side is on opposite side to the higher priority group on the other side. Opposite means E, and so this is the E compound. We can fill out the rest of our UPAC name. Now the other possible stereoisomer of this compound, if we keep the left-hand side the same, but then we flip the other side, so the fluorine is at the top here and the hydrogen is at the bottom, then we're going to have the highest priority groups on the same side. So that is going to be the Z isomer of that compound. Okay, and now this should show you why we need the EZ system. We couldn't assign cis or trans to these compounds because how would we know what the cis or the trans applies to? Are we talking about the carbon versus the fluorine, or are we talking about the iodine versus the fluorine? So we need this EZ nomenclature for compounds that have more than two substituents. Okay, now as I said, if you can't decide based on the first atom you get to, you need to expand out along the chains and find the first point of difference. So here we've got a molecule where if we split it once again, we've got on the left-hand side, we've got carbon versus hydrogen. That's very straightforward. Carbon is higher priority. But then on this side, we've got, on the right-hand side, we've got a carbon here versus a carbon here. So let's look at expanding out this side first. We expand that out and we end up with expanding it to 2 hydrogens and an oxygen. So there's our 2 hydrogens and our oxygen. The oxygen is then higher priority. Then on the other side, when we expand it out, we have 2 hydrogens and a carbon. Hydrogen, hydrogen, carbon. The first point of difference is oxygen here versus carbon here. This is higher atomic number, so it gets the higher priority. Highest priority is on the same side, so it's the Z isomer. Now, we need a system for dealing with multiple bonds because they're going to change one substituent relative to another in terms of its priority. So all we do is we replicate the atoms that are attached to an atom that's part of a multiple bond. So we could also sometimes call these phantom atoms. So here, if we have a carbon-carbon double bond on a substituent, each one of the pi bonds gets turned into phantom or dummy atoms attached to those elements, so that when we're assigning priority, we draw out something that looks like this, where we've got these phantom or dummy carbon atoms in place of the multiple bond. And so that means that when we have a ethyl group versus an ethynyl group, the ethynyl group is going to be higher priority because of these phantom atoms that we've got through this expansion. And then if we look at an alkyne, that's going to have 2 sets of phantom atoms on each of the carbons involved in the triple bond. And so that's going to be an even higher priority than a alkene group of the same type. And so if we look at this molecule here, hydrogen versus carbon, very straightforward, that's the higher priority. But if we look at the alkene versus the alkyl group, the dummy atoms on these carbons here are going to mean that when we expand this, we're going to have a carbon atom here, whereas we're only going to have hydrogen atoms here. And so this will end up being the higher priority, and therefore this is the E-configured alkene. Okay, so let's go through one more example. Here's an alkene. We're going to assign the name to this structure, including the E or the Z nomenclature. So first off, let's break the molecule into 2. So we've got the left-hand side is just a carbon atom versus a hydrogen atom. So the carbon atom is going to be the higher priority. And then on the other side, we're going to have a carbon atom here versus a carbon atom here. And so we're going to have to go further out along the chain. Here, this is going to expand to a carbon plus a hydrogen and a hydrogen. And so that's going to be different to when we expand the alkene, which is going to have these dummy carbon atoms put in. And so on the top side, carbon atom 5 is going to be expanded to a carbon, a hydrogen, and a hydrogen, whereas this atom over here is going to be expanded to a carbon, and a hydrogen. And so that is going to be the higher priority, and so that becomes number 1. And so now we've got the highest priority groups on the same side, so it's going to be the Z alkene. Okay, now this idea of geometrical isomers or stereoisomers of alkenes is also important in terms of their properties. So cis and trans double bonds have different properties. And in general, cis alkenes are less stable than trans alkenes, because in a cis alkene, we've got the 2 groups on the same side of that double bond, and the double bond, we can't rotate around that pi bond. And so those 2 groups are being held near to each other. Each of those groups has an electron cloud. That electron cloud can sort of repel, each electron cloud can repel each other. And we call that steric repulsion. And so this is a steric hindrance, or sometimes repulsion. And it's where 2 groups just don't want to occupy the same space because of their electron clouds. And so cis alkenes are generally less stable than trans, where trans have those groups, those large groups, further away from each other. So this group is now opposite to this group, and the repulsion between this hydrogen and this methyl group is not nearly as much as between two methyl groups. Now, the structure also affects the physical properties. So the boiling point of methyl propene, which is a 4-carbon alkene, is different, very small difference, but it is different to 1-butene. And cis 2-butene is different again, and cis isomer of that compound is different to the trans isomer in terms of their boiling point. So there's not a large difference, there are differences in the physical properties of those molecules, and there's a difference in the chemical reactivity as well. Okay, if we have an alkene that has more than one double bond, that's possible. If it's double bonds that are isolated from each other, so in this case we've got a double bond here, and a double bond not directly adjacent, but some number of carbon atoms away, we call those double bonds isolated. So there's more than one single bond between each of those double bonds. Now, if we only have one single bond between double bonds, then we call these systems conjugated, and they have special properties. So these are very special, and they have properties that are different to isolated double bonds. And the rarest type of polyalkenes or polyenes are the cumulenes or cumulated double bonds. So that's where we have double bonds that are directly adjacent to each other. So there's 0 single bonds between each of the double bonds. And these molecules, simple cumulenes, are actually quite important in astrophysics. They're actually present in the universe in places where there's a relatively large abundance of carbon and not much hydrogen for it to bond with, and you get these unusual cumulene structures out there in space. Now, a little bit more about the nomenclature of these unsaturated systems. If we want to name these compounds, we find the longest chain first, and we enumerate the carbons so that we include the functional group. In this case, we're talking about the double or the triple bond. And we give it a numbering system so that the double or triple bond gets the lowest possible number. So we start numbering from the end closest to that group. And then we put the substituents on that parent longest chain and number them according to which position on the chain they are. The suffix for an alkene is -ene, and if we have more than one alkene, then we can say di, tri, tetra, and so on. And so this compound, we've started numbering at this end because it's closest to the first alkene. So it's a 1 and then 3 diene. So it's 1,3 heptadiene because it's a 7-carbon chain. And at the 5 position, there's a methyl group. So it's 5-methyl 1,3 heptadiene. This one here, we've got, we can number from either end because it's symmetrical, and we would get to 2 here and 4 here, so it's a 2,4 hexadiene. And I'll leave it to you to work out whether that's E or Z at each one of those double bonds. For alkynes, it's really analogous, so we name them exactly the same way, but instead of an alkene, we name it as an ine. So this molecule here, we started naming at the end closest to the alkyne. So this becomes 1, this becomes 2, 3, 4, 5, 6. So it's a hexine. The triple bond starts with the 2 position, so it's a hex 2-ine or a 2-hexine, and it has a methyl at the 5 position, so it's 5-methyl hex 2-ine. And you'll often see this also written as 5-methyl 2-hexine, which I actually prefer, but you'll see both ways of naming these things. And then similarly, this compound here, we've started numbering here, 2, 3, 4, 5. We've got a 5 bromine, so it's a 5 bromo, 6, 7, 8, so it's an oct as the stem, so it's 5 bromo oct 3-ine as the name of that compound. Okay, so that's that really gives you a bit of an insight into alkenes and alkynes, their structure, a little bit about the stereochemistry of alkenes, and particularly important is that EZ. Remember, Z is for the same side. They're on the same side. and E is on opposite sides. And remember those priority rules. We go atomic number, higher the atomic number, the higher the priority, and we work out along equivalent chains until we find the first point of difference, putting in those dummy atoms if we find multiple bonds. Okay, so hope that helps, and good luck with your alkenes and your alkynes.